this width of depletion region, the width of depletion region for in unbiased condition is given by W equal to 2 epsilon V naught by Q into 1 by Na plus 1 into 1 by Na plus 1 by Nd whole root over 2 epsilon V naught by Q into 1 by Na plus 1 by Nd. If you reverse bias the diode by voltage V, then in formula of depletion width V naught is replaced by modulus of V naught plus V. Depletion width increases with reverse and decreases with forward biased. Depletion approximation is assumed in calculating the above equations. Charge neutrality equation xn naught Nd equal to xp naught Na, also xn naught plus xp naught equal W. Xn naught Nd equal to xp naught Na, also xn naught plus xp naught equal W. For a linearly graded junction with the charge density increasing linearly from P region to N region as P equal to alpha Qs Qx, the depletion width is given as W equal to 12 epsilon V naught by alpha Q whole power 1 by 3. The cube root 12 epsilon V naught by alpha Q. Alpha Q is the denominator, 12 epsilon V naught is the numerator. Alpha means impurity gradient, Q means charge of electron, epsilon means permittivity of material, V naught means contact potential. Maximum electrical field for such a junction is given as modulus of Emax equal to alpha Q W square by 8 epsilon. Current equation IF equal to I naught into e power Vd by eta Vt minus 1. I naught means reverse saturation or leakage current, Vd means forward biased voltage, eta means recombination factor, material constant equal to 1, for germanium equal to 2 for silicon. Vt means thermal voltage, Vt equal Kt by Q, 0.0259 volts at room temperature. Next, IF means the majority carrier current and diffusion current, I naught means drift current, reverse saturation current. I naught doubles for every 10 degrees centigrade rise in temperature. I naught of T2 equal to I naught of T1 into T power T2 minus T1 by 10. I naught of T2 means reverse saturation current at temperature T2. I naught of T1 means reverse saturation current at temperature T1, T2 greater than T1. I naught depends on temperature and is minority carrier current. IF forward diode current is independent of temperature. Forward voltage across diode decreases with the temperature. For 1 degree centigrade rise in temperature, it decreases by 2.5 millivolt. dV by dt equal to minus 2.5 millivolt per degree centigrade. I naught equal to AQ Ni square into dP by Lp Nd plus dN by Ln Na, where A means area of cross section, dP dN means diffusion constant of holes and electrons respectively, Lp/Ln means diffusion length of holes and electrons respectively. Diode resistance, dynamic or incremental resistance of diode R equal to eta Vt by If, that equal to dV by di, where eta means recombination factor of equal to 1 for germanium, equal to 2 for silicon. If means forward current, Vt means thermal voltage. Static resistance R equal to V by I. Static resistance is always greater than ACR dynamic resistance. Junction capacitance Cj equal to A epsilon by W, where A means area of cross section of diode, W means width of depletion region, epsilon means permittivity of material. Depletion layer in a PN junction behave as a parallel plate capacitance, and capacitance is given by Cj equal to dq by d of V naught minus V, that equal to A by 2 into root over 2q epsilon Na Nd whole by V naught minus V into Na plus Nd. 2q epsilon Na Nd అనేది numerator, V naught minus V into Na plus Nd అనేది denominator, where V means applied voltage, A means area of cross section, Cj is directly proportional to 1 by V naught minus V whole power 1 by 2. Cj is voltage variable capacitance. In case of reverse bias junction capacitance, Ct is same as junction capacitance, transition capacitance Ct. In case of reverse bias transition capacitance, Ct is same as junction capacitance. In reverse bias diode transition capacitance varies as Ct is directly proportional to V power minus N, V power minus N, where V means applied reverse voltage, N means 1 by 2 for step graded diode, P plus N or Pn plus equal to 1 by 3 for linear graded diode, P plus N plus equal to 1 by 2.5 for diffused PN junction diode. Diffusion capacitance or storage capacitance CD. CD is junction capacitance in forward bias diode. CD greater than CT always. CD less than directly proportional to root doping. CD directly proportional to IF. CD equal tau into Z, where tau is the mean lifetime of minority carriers on either side or time constant of diode. G means dynamic conductance of diode. G equal to IF by eta Vt. CD equal tau IF by eta Vt farads. Diffusion capacitance of diode when it is operated with the sinusoidal signal CD dash is CD dash equal to half into tau into Z at low frequency. At high frequency CD dash equal to tau by 2 omega whole power 1 by 2 into Z, where omega means angular frequency, tau means time constant of diode, G means dynamic conductance of diode. Metal semiconductor junctions. Metal semiconductor junctions are of two types: ohmic contact and Schottky junction. Band profile of disconnected material and semiconductors can be drawn, where phi m means work function of metal, xi s means electron affinity, EFM Fermi level of metal, EFS Fermi level of semiconductor, ECEV conduction of valence and conduction valence levels respectively. Formation of Schottky junction takes place when metal and semiconductor are brought together. The difference between PN diodes and Schottky diodes can be tabulated as the forward bias needed to make the device conducting cut-in voltage is large. PN diode, Schottky diode ki cut-in voltage is quite small. PN diode ki the reverse current is due to minority carrier diffusion to the depletion layer and strong temperature dependence. Schottky diode ki the reverse current is due to majority carriers that overcome the barrier, hence weak temperature dependence. PN diode ki the forward current is due to the minority carrier injection. Schottky diode ki the forward current is due to majority carrier injection. PN diode ki switching speed is controlled by recombination of minority injected carriers. Schottky diode ki switching speed is controlled by thermalization of hot injected electrons across the barrier. PN diode ki ideality factor in IV characteristics is 1.222 due to recombination depletion region. Schottky diode ki essentially no recombination depletion region. Ideality factor is nearly equal to 1. Heavy doping in a semiconductor causes a very thin depletion width. Electron can tunnel across the barrier leading to ohmic behavior. Current is linear in ohmic contact. Semiconductor devices. Photoconductors. When light falls on semiconductors, its conductivity increases, and this property is called photoconductive effect. This is also called photoresistive effect. The minimum photon energy required for intrinsic excitation from VB to CB is energy gap EZ. Extrinsic excitation from donor level to CB or from VB to acceptor level requires lesser energy than energy gap. Photoconductive equation is given by EZ equal to h mu equal to hc by lambda. H means Planck's constant, c means speed of light in free space, lambda means wavelength of light incident on SC. Wavelength of light incident can be given as lambda equal to 1.24 by EZ in electron volts. LED, light emitting diode. It works on the principle of electroluminescence. It is fabricated using direct band gap material. It will emit light when properly excited. It emits light due to a large number of recombinations at junction. Color of light depends on the concentration of dopant. It is always operated under forward biased. With a forward current of 20 milliamps, LED gives out the maximum intensity of light. In reverse bias, it works like a normal diode. Power dissipation LED of the order of milliwatt. Response time is in microseconds. Operating lifetime is 100,000 hours. Cut-in voltage is 1.3 volts. It is used in remote control as a display device and is designing of optocouplers. LCD, liquid crystal display. Operating principle is dynamic scattering of light. Power dissipation is the order of microwatt. Response time is milliseconds. Operating life is 50,000 plus hours. It is used as a display device. Material used is liquid crystal that are activated by electric current. LDR, light dependent resistor, also called photoresistor, or light activated resistor, LAR. Principle of operation is photoresistive effect. Range of resistance is 5 ohms to 0.75 ohms. Dark resistance of LDR is 0.75 mega ohms. It is used in optocouplers. Material used for fabrication are CDS and SC. LDR lo CDS, SC, LDR, CDS, SC, LDR, CDS, SC. Photodiode. Principle of operation is photoconductive effect. Photosensitive material used are CDS, ZE, ZNS, SC. It is also called light operated switch. Germanium photodiode responds to visible light while silicon photodiode responds to infrared light. Photosensitive coating is provided at junction only. Compared to normal diode, photodiode has larger depletion width obtained from lower level doping. It is also operated under reverse bias condition. Compared to normal diode, it is 10 times faster, 100 times higher sensitive, but power handling capacity is low. Magnitude of photocurrent increases with increasing intensity of light falling at junction. Current in photodiode is given by I equal to Is plus I naught into 1 minus e power V by eta Vt, where Is means short circuit current for a photodiode, I naught means reverse saturation current, V means voltage applied, Vt means thermal voltage. Photocurrent flows from N to P. Photocurrent is a minority carrier current. It does not provide gain. Photocurrent is a diffusion current. It is used in remote control sensors, in designing of optocouplers, and to read audio track recorded on motion picture film. When photodiode is forward biased, it behaves as a normal diode, and effect of light on current is zero. Avalanche photodiode APD. Basically a photodiode along with avalanche effect. APD can handle large amount of power compared to PD photodiode. Its response time is smaller than PD. APD is widely used in fiber optic communication because of its high sensitivity. Zener diode operates on the principle of tunneling effect, always operated under reverse bias, mainly used in voltage regulation application, maintains constant voltage across a load if properly biased. Phototransistors, its principle of operation is photoconductive effect. Coating of photoconductive materials is done at collector based junction. It is basically a light operated switch. NPN phototransistor is faster than PNP phototransistor. Solar cell, its principle is operation is photovoltaic effect. Terminal of voltage of solar cell can't exceed the barrier potential of diode. That's why an array solar cells is used to achieve higher voltage. We can measure terminal voltage of solar cell using voltmeter. Popularly used solar cells are SC cells, NICD cells, PBS cells. NICD cells are rechargeable cells used in satellites. Nickel cadmium cells are rechargeable cells used in satellites. It is used as in automatic traffic signal lightning, generally operated under open circuit condition. It can be operated in forward biased condition and has cut-in voltage equal to 0. The photocurrent of solar cell IL equal to QGLA, economics bracket open, W plus NL plus LP. QGLA into W plus LN plus LP, where GL equal to optical generation rate, A equal to area. Net current of solar cell I equal to I naught into E power eta by eta Vt minus 1 minus IL. Wave characteristics of solar cell lies in the fourth quadrant, like circle, quarter circle. Solar cell is operated in the fourth quadrant. The product Vi is negative, which implies that solar cell is acting as a source of energy. ISC equal to minus IL equal to minus QGLA into the bracket open chesi W plus LN plus LP. VOC equal to eta Vt naught eta Vt into natural log 1 plus IL by I naught. Conversion efficiency of solar cell, the ratio of electrical output power and incident optical power. Fill factor of a solar cell FF equal to VMIM by VOC into ISC. Practically fill factor is approximately 0.7 and maximum efficiency is 25%. Optocouplers, these are optically coupled but electrically isolated. Optocouplers are faster than conventional devices, widely used in industrial applications where very good DC isolator better than transformers are required. Tunnel diode, it is fastest switch. Its response time is of the order of picosecond. It is a P plus N plus diode having doping level of 1:10 power 3. Works on the principle of tunneling effect. It exhibits voltage control, negative resistance. It has very narrow depletion layer, 100 Armstrong units to 200 Armstrong units. It is used as a linear device as well as negative resistance device. Best material is gallium arsenide having highest swing. It is used in designing microwave oscillations or as a relaxation oscillator in designing of pulse and switching circuits and as parametric amplifier. Pin diode, it is P plus IN plus diode. I represents intrinsic material. If I is replaced by P type, then called P pi N diode, and if I is replaced by N type, then it is called P gamma N diode. Pin diode is lightly doped intrinsic semiconductor sandwiched between highly doped P and N. It has low response time because of highly resistivity of I region. It is a 2-terminal 3-layer having single junction device. It is always operated and under reverse biased condition. When whole I region is converted by depletion layer, then it is called a swept out condition. In PIN diode, if whole I region is not swept out, then signal loss will occur. It is used in handling microwave power as microwave mixer, as a duplexer, in designing of transmit receive switch, in designing of anti transmit receive switch. Laser stands for light amplification by stimulated emission of radiation to source of coherent light. It is fabricated with direct band gap materials having larger carrier lifetime. Emission in laser is both spontaneous and stimulated. Population inversion occurs in laser. Lasers are highly directional. Example, helium neon laser. Varactor diode. PN junction diode that changes its capacitance as bias applied to the diode is varied, operated under reverse bias, used mainly in tuning application and in low noise microwave devices. C is directly proportional to 1 by junctional potential whole power m. M equal 1 by 3 for linear graded junction, M equal 1 by 2 for abrupt junction. Used as a low noise amplifier, in brackets parametric amplifier. Bipolar junction transistor. BJT junction transistor characteristics. Bipolar junction transistor was invented by William Shockley, Brattain and Bardeen. Current flows both due to majority as well as minority carriers, that's why called bipolar device. It is a current control device, noisy device due to presence of minority carriers. Thermal stability is lesser because of leakage current or reverse saturation current. Doping in emitter is highest and base it is lowest. The area of collector is highest and that of the base is lowest. Transistor action takes place in Bose region. Saturation, active amplifier, reverse active attenuator. A transistor has excellent transistor action if emitter is heavily doped in comparison to base. Base width is kept much smaller than diffusion length of carriers. Current in BJT, collector current in transistor is given by IC equal beta IB plus beta 1 plus beta plus 1 into IC naught. IC equal beta IB plus beta plus 1 into IC naught. This equation is valid in active region. Beta means current gain of common emitter. Power dissipation in a transistor is given by PT equal to modulus of IC into modulus of VCE, where IC is collector current, VCE means collector to emitter voltage. Power dissipation in saturation and cutoff region is almost zero. Power dissipation is maximum in active region. Emitter cutoff current ICB0 is given by ICB0 is approximately IC0, but actually it is slightly greater than IC0. Base current cutoff ICE0 is given by ICE0 equal to beta plus 1 into IC0. IC0 is reverse saturation current across reverse bias transistor collector current. ICB0 greater than ICE0 is greater than ICB0 is greater than IC0. Current gain of a common base alpha is given by alpha equal to IC by E modulus equal beta by beta plus 1, where beta is a current gain of the common emitter. Beta in terms of alpha is given as beta equal to alpha by 1 minus alpha. Current gain of common collector gamma is given by gamma equal to beta plus 1 equal to 1 by 1 minus alpha. Beta for DC analysis greater than beta for AC analysis, that is beta DC greater than beta AC, or HFE greater than HFE, capital HFE greater than small HFE. Emitter injection efficiency gamma E is given by gamma E equal to IEP by IEP plus IEN. IEP plus IEN is the denominator part for NPN transistor. Gamma equal to IEN by IEP plus IEN for NPN transistors, where IEP means emitter current due to holes. IEN means emitter current due to electrons. Base transport factor B is given by B equal to IC by IEP for NPN transistor, B equal to IC by IEN for the NPN transistor. Current gain alpha in terms of gamma E, and B is given as alpha equal to B into gamma E. Value of gamma E and B is very close to 1, and in ideal conditions it is 1. In diffusion transistor, base current is only to diffusion. In drift transistor, base current is due to diffusion and drift phenomenon. Recombination agent used to trap charge carriers is gold. Earlier effect, increase in depletion region width due to increase in reverse bias across collector base junction is called early effect. Due to early effect, effective base width decreases. Due to early effect, alpha increases by little amount but beta increases by a large amount. The effective base width offers a spread resistance at higher frequencies. Emitter junction breakdown voltage is similar than the collector junction breakdown voltage. Emitter junction breakdown voltage is smaller than the collector junction breakdown voltage. Emitter junction breakdown voltage is smaller than the collector junction base voltage. Emitter junction breakdown voltage is due to Zener effect, while collector junction breakdown is due to avalanche effect. Field effect transistors. FET, it is a voltage control device. It is a high impedance device. It is a majority carrier device. It is less noisy than BJT. It is thermally stable. It is smaller in size compared to BJT. Leakage currents are zero. It is unipolar device. FET is a symmetrical device where drain and source can be interchanged, while BJT is a symmetrical device. JFET channel is wedge-shaped. Process of varying channel width by variation of VDS is called channel width modulation. In N-channel JFET channel width is narrower near drain. MOSFET is a voltage control capacitor. VCC, input impedance of MOSFET is greater than JFET. MOSFET is basically a capacitor. Internal power consumption of MOSFET is very low. MOSFETs are less noisy than FET. MOSFETs are faster than JFETs. MOSFETs are faster than JFETs. MOSFETs are faster than JFETs. Wrong. BJT is faster than FET devices, but its power consumption is large compared to FET devices. JFET parameters in saturation region, current through FET is given by IDS equal IDSS into 1 minus VGS by VP whole square. IDSS equal to saturation current at VGS equal to 0. VP means pinch off voltage. IDS means saturation current at any VGS. IDS varies parabolically with respect to VGS. Amplification factor M is given by mu equal to RDGM, where RD means drain resistance, GM means transconductance. Transconductance GM is given by GM equal to minus 2 IDSS by VP into 1 minus VGS by VP. GM equal to minus 2 into IDSS by VP into 1 minus VGS by VP. GM equal to minus 2 into IDSS by VP into 1 minus VGS by VP, or GM equal to 2 by modulus of root VP, 2 by VP into root over IDS into IDSS. Numerator part 2 into root over IDS by into IDSS whole by modulus of VP. General equation of our gate to source voltage is VGS equal to VP into 1 minus root over IDS by IDSS. FET has a voltage dependent resistor. JFET has a major application as voltage dependent resistor. RDS equal to RDS on by 1 minus W by A. RDS on by 1 minus root over VGS by VP, where RDS on equal to channel resistance when full channel is available for conduction. A means half channel width. V means effective channel width. If VGS equal to VP, then depletion region fully occupies channel and channel becomes pinched off. VP equal to A square QND by 2 epsilon పక్కన separate లో minus V0 for P plus N junction diode. For P plus N gate channel junction, VP equal to A square QNA by 2 epsilon minus V0 for PN plus gate channel junction. When VGS is varied from 0 to VP, RDS varies from RDS on to infinite. MOSFET metal oxide semiconductor FETs have a very high input impedance. MOSFET is used as a voltage control capacitor. MOSFET have very high switching speed. Gate capacitance is given by C gate equal to Cox into W into L, where Cox equal to 3.45 into 10 power minus 11 by Tox. C gate means gate capacitance. W, L means width and length of gate plate. TOX means oxide layer thickness. COX means oxide capacitance. MOS capacitor can be operated in 3 modes: accumulation, depletion, inversion. CV characteristics of MOS: low frequency characteristics, accumulation, depletion, inversion. VF means flat band, VT means threshold voltage, VG means gate voltage. The drop in the capacitance is due to formation of depletion capacitance in series with the oxide capacitance. If C0 is known, oxide layer thickness Tox can be found as Cox C0 equal to epsilon ox A by Tox. Tox equal to epsilon ox C0 into A, where Cox epsilon ox equal to oxide permittivity. If C minimum is known, maximum depletion width WD max can be found. C minimum equals C0 CD minimum by C0 plus CD minimum. CD minimum equal to epsilon SI into A by WD max. WD max equal to epsilon SI into A by CD minimum, where epsilon SI means silicon permittivity. CD minimum means minimum depletion layer capacitance. MOSFET configurations. MOSFET current equations n channel MOSFET లో cutoff means VGS greater than or equal to VTN, IDS equal to 0. Linear or triode, VGS greater than VTN, VDS less than or equal to VGS minus VTN, then IDS equal to mu n COX into W by L into VGS minus VT into VDS minus VDS square by 2. Very, very important. Cutoff means VGS greater than or equal to VTN, IDS equal to 0. Linear or triode means VGS greater than VTN is the condition and VDS less than or equal to VGS minus VTN, then IDS equal to mu n COX W by L into VGS minus VTN into VDS minus VDS square by 2. Saturation means VDS greater than VTN and VDS greater than VGS minus VTN, VGS greater than VTN and VDS greater than VGS minus VTN. IDS equal to half mu n COX W by L into VGS minus VT whole square into 1 plus lambda VDS into 1 plus lambda VDS. Lambda means channel length modulation parameter, VTN means threshold voltage, mu n means electron mobility, COX means oxide capacitance, W, L means width and length of the MOSFET. P channel MOSFET, same. Cutoff means VSG greater than or equal to VTP, ISD equal to 0. Linear triode means VSG greater than VTP, VSD less than or equal to VSG minus VTP, ISD equal to mu p COX W by L into VSG minus modulus of VTP into VSD minus VSD square by 2. Saturation VSG greater than or equal to greater than VTP, VSG greater than VTP, VSD greater than VSG minus modulus of VTP, ISD equal to half mu p COX W by L VS minus VTP whole square into 1 plus lambda VDS, where VTP means threshold voltage, mu p means whole mobility. VTN is positive and VTP is negative. For a MOSFET operating in saturation region, channel length modulation effect causes decrease in output resistance. In triode region, FET works as voltage variable resistor. Transconductance GM equal dou ID by dou VGS. For depletion MOSFET, channel is diffused and current flows even if VGS is 0. It operates in two mode operation, depletion mode and enhancement mode. For VGS less than the threshold voltage, it works in depletion mode, and for VGS greater than threshold voltage, it works in enhancement mode.